Hi, how do you do? Before we finish this chapter, it's important that we talk about dispersive media. When light travels in a vacuum that's so at speed c, doesn't matter the frequency of the electromagnetic wave, it will travel at c. But when light enters a medium, this one affects the speed of propagation of light. Light will not travel at c anymore. It will travel at c over n, where n is the index of refraction. But some media have different index of refraction for different frequencies. This we call dispersive media, which most media are a bit dispersive. If you make a race between a red and a green laser on a dispersive media, they won't reach the end at the same time. Now, interesting things happen when, instead of a well-defined monochromatic wave, what you have is a pulse of waves. Pulses of waves are the results of interfering a wide range of frequencies. If you interfere two waves of the same amplitude but slightly different frequencies, you will obtain a train of pulses. Assume you have a wave E1 with omega 1 and K1, and a wave E2 with omega 2 and K2. The resulting wave will be E1 plus E2. Well, we can use some trigonometric identities again to get Let me define omega p and omega g, where subindexes p and g will make sense later. So omega p is the average of both angular frequencies, and omega g is half their difference. Then the resultant wave is, which is the product of two cosines, one involving frequency p and the other involving frequency g. Look here that omega p is much larger than omega g. If you plot this resulting wave, you will find that you have a fast oscillation and a slow oscillation. The slow oscillation is the envelope of the fast oscillation. You have a train of pulses, you have beats. If you interfere 3, 4, 5 waves with slightly different frequencies, they will all interfere constructively at some points, but destructively at others. You will have a train of more defined pulses. The more frequencies you use, the more defined those pulses will be. This is something you can simulate easily with Excel, MATLAB, or Python, for instance. Well, if these electromagnetic waves are in a vacuum, these pulses will propagate at c, preserving all characteristics. But if they travel in a dispersive medium, the speeds of the different frequencies will be different, and the constructive and destructive interference will shift. Using the relationship between velocity, angular frequency, and wave number, we define the phase velocity as omega sub p over k sub p, and the group velocity as omega sub g over k sub g. These names will be clear in a while. But the phase velocity will be related to the velocity of the phase of the waves. With the fast oscillations in the wave packet, the group velocity will be related with the propagation of the slow oscillations, with the velocity of the packet as a whole. We can assume that the differences between frequencies and wave numbers are small, so we can approximate them as And because omega is kVp, the phase velocity is c over n, and n depends on the frequency. Deriving with respect to k, and with k equal to 2 pi over lambda, so we have that the group velocity is the phase velocity plus this term that depends on the dispersion of the medium, dn over d lambda. For non-dispersive media, both are the same. For dispersive media, the group velocity can be larger or smaller than the phase velocity. Here we will have that the phase of the wave inside the wave packet will shift forward or backward with respect to the packet itself. The packet is who carries the energy. It is the one that we can measure its speed, but the phase can be interesting in further interference phenomenon. For example, a photon that we imagine of a specific frequency, it is actually a wave packet, so it is made of a range of frequencies. Two photons of the same wavelength can be made non-identical if we change the phase of one of them. And this can have interesting quantum interference properties that we will talk about later in this course. One can also play with the medium and get a group velocity almost zero. You can also find phase velocities faster than c. But this does not violate special relativity, as that can't be used to transmit information. It is not light or matter actually moving faster than light. Well, see you in the next group of lectures, and may science be with you.